Okay, yeah, sorry I'm late. Let's start. Do you have any questions? Okay, so I guess to kind of put a focus on what we do on chapter 4, all right? So chapter 4, kind of just to sum up, we go over section 4.1 to 4.4. But I just want to highlight, like, kind of from the point of view of what you need to be able to do. All right, what is it that I expect you to know how to do on the exam and things like that. So let's go to the homework. Okay, so for example, right, you should be able to, or you must be able to do these kind of problems from 1 to 14 on 4.2. Yeah, Saga, we're gonna learn a lot of things from now until next week, right? Stay tuned for more details. So, all right, so 4.2, this is the kind of problems you must be able to do, okay? And that just basically mathematically solving equations. 4.3, okay, going down, 4.3, you must be able to solve these kind of problems. And that's it, right? And I guess that's 4.1 too. But in terms of like the physics and the interpretation of what the system means, that's something I want to lecture, right? Because it really is an important aspect of these lectures. But I don't think like there's enough room for reasonable questions to be asked on this content, like, you know, resonance, beat, and that kind of thing. So, right, there will be a lecture part where I give the interpretation on these things. But in terms of problems, right, you must be able to solve these questions completely, like the ones I just highlighted so far. And of course, like there'll be assigned for you as homework. So any question on this? Like, in other words, any questions in here that you think you do not know how to solve, and then you want me to do a couple of examples just to make the point. Yeah. Okay. So okay, sure. We'll do one of each. That sounds good. IVP. That sounds good. Right, Carl. That's right. The physics things won't be on the final, unless you want one for yourself. Then I'll, you know, make a special question only for you. Okay, so one of each. All right. So let's try. Let's try IVP. Okay. Let's try IVP, and we'll do one of each. So let's see here. Do one. Let's do number 11. All right, on 4.2. Which is y double prime plus 6y prime plus 8y equals cosine of t. And then, you know what? Let's do number 12. It looks more interesting. Is 2 cosine 3t. Okay. And y of 0 equals y prime of 0 equals 0. Okay. So I will not do problem for 4.1. All right. I mean, these are just different variations, and I hope you can handle it for yourself. So for this one, right, so first you approach it with the homogeneous equation. So lambda squared plus 6 lambda plus 8 is equal to 0. That's 4 and 2, right? So lambda plus 4, lambda plus 2 is equal to 0. So YH is C1 e to minus 4t, C2 e to minus 2t. Okay. Then you take care of the particular solution, right? I don't know. I feel like the A and B approach are cleaner. All right. I know the book like complexification. I would just stick with the A/B approach. You pick. All right. So our YP will be A cosine 3t plus B sine 3t. Now let me pause and say something like this, right? Of course, one of the big issue, right, of 4.1 to 4.3 is how to guess the right form of YP. The difference between 4.2 and 4.3 is that 4.2 always has damping coefficient, whatever that means, like the middle term right here, the Y prime. Well, 4.3 has no damping coefficient. So in terms of guessing, right, YP for the 4.2, what you have to worry, right, is once in a while you have to see if there's a T required. In this situation, right, with cosine and sine forcing function, will you have to worry about T for these situations in 4.2? Like, will you have to worry that there's a T like this in 4.2? That's right, right? For 4.2, there's no T. The reason is because of this, right? Mathematically, you will never have pure cosine and sine solution. You might have cosine and sine, but there will be exponential outside. All right, like the real part of your solution will never be 0, even if you have complex roots. So that's why you will never have coincidence. From the physics angle, which is a little bit more, interesting because I like to approach from the math, if there is a damping coefficient, you will never have resonance. So either way, right? This is the guess for 4.2. As long as there's a damping coefficient, okay, you will never have coincidence. So anyway, now just purely plug in, right? So I should be mindful of myself. YP prime is 3 minus 3 A sine, right, 3t plus 3b cosine 3t, and double prime will be minus 9 cosine minus 9 sine, right? And I need to kind of put in a coefficient just so that I don't forget. 6, so that will be minus 18, right? 18. Okay, so having that, okay, so I add them up. Let's see here. Plug in. So cosine, I have minus A plus 18b, right? And that is going to be equal to 2 because I have 2 cosine 3t. And then in terms of sine, I have minus b minus 18a. That would be 0, right? So all in all, do I know what's going on? I just don't like to multiply 18 with 18, but yeah, I guess I have to. Minus a plus 18b is 2. What's 18 squared? 180 plus 180 plus what? Oh my gosh. Does anyone know what 18 squared is? 10 squared plus 64 plus 80, right? 160. That is 100 to 160, 324. I hope I'm right. Okay, appreciate it. So multiply with 18, right? Minus 324. Why is this so weird? Equal to 0. Did I make a mistake somewhere? How come this problem just comes out to be so strange in terms of numbers? So anyway, right? So here, then A will be add up, right? You got minus 2 over 325. Oh, right? And then B is obviously, right, from this equation, minus 18A, so 36 over 325. Any mistake somewhere? I think that looks okay, right? Because of this, right? Did I make any arithmetic mistake? My procedure is correct, but I'm not prone to, I'm not immune from arithmetic error. So anything? Because the number looks like not nice, so I'm a little suspicious. But okay, so all right, so we got YC, we got YH, we got YP. It's a it's a initial condition, right? Problem, IVP problem. So we need to solve for the whole thing. So YT is C1. What is it? E to a minus 4t plus C2 e to minus 2t plus, rather minus, right? 2 over 325 cosine 3t plus 36 over 325 sine 3t. Okay. Now I need to solve for C1, C2. So y of 0 is C1 plus C2. It just gets equal to 0. Y prime of 0 is minus 4C1 minus 2C2. Derivative of cosine, I don't have to care because it becomes sine. So the other one, right, it will be 3, so plus 48 over 325 is equal to 0. Wait, it's not 48, 36 times 3. It's not 16 times 3. 108, right? So what is it, right? Let's say multiply the first equation by 4. 4C1 plus 4C2 minus 8 over 325 is equal to 0. Minus 2C2 plus 108 over 325 is equal to 0. Add them up, right? I got 2C2 plus 100 over 325 is equal to 0. C2 is minus 50 over 325, which simplify to blah, blah, blah. And I'm too lazy at this point. C1 is blah, blah. Is that okay? Any question? All right, so that's one example from 4.2. From 4.3, let's take a look at question 12. Okay, where we got y double prime plus 9y is sine 3t. And initial condition is y of 0 is 1, y prime of 0 is minus 1. Okay. So the homogeneous, right, is lambda squared plus 9. Lambda is equal to 0, which means lambda is plus minus 3i. So your YH is C1 cosine 3t, C2 sine 3t. So what's your YP? Your YP here takes what kind of guess? Oh, I apologize, right? I know my solution is 9. Yeah, thanks. I got the right solution. I just got the wrong form. 9. Yeah. Is it okay? So what's the YP? Correct. Right here exactly is the difference. Well, it doesn't have to be always, okay? But I picked this particular problem because of the t in front. Okay? I picked this particular problem because of the t in front, because of the coincidence, right, between the homogeneous solution and the form of the particular solution. All right. Well, of course, right, doesn't have to be always the case, but this is a possibility in 4.3, and I picked a problem that demonstrates that. Okay. So, for example, right, if this is like a 4, for example, okay, if this is a 4, yeah, there's no damping and there's resonance. No damping by itself doesn't qualify it. Okay. For example, if it's a 4 right here, then right, this will change to a 4, and this will change to a 2, right? And then this will change to a 2. And then there's no T. Is it okay? Okay. But right here, the problem is a 9. So there is a resonance going on. So there must be a T. All good? So correct. But you know, it would be a bit slightly painful to plug in this thing, all right? Because there's just going to be a lot of terms, right? And this probably is where the complexification approach might be more pleasant than this. I don't know, right? This you imagine, right? You expand it, you got a lot of terms you have to keep track of. While if you do complexification, you just have to keep track of half of the terms. Okay, so your pick, right? But still, when you go with the complexification approach, you still need to have a t in front. Okay, I'll stick with this. So now plug in, right? Plug in. So first, right, yp, so 9yp, right, is 9 of, right, at cosine 3t, 9b sine 3t. And then y prime, which I don't care about because it's not there, but so that's minus, oh my gosh. So first, differentiate the t, gives me a cosine 3t plus b sine 3t. And differentiating the, oh, sorry, I missed a t here, right? And differentiating the cosine sine terms give me what? Plus t, right? And then I got minus 3 sine 3t plus 3 cosine 3t. Oh, I missed a and b, right? So put that in. Okay. And now I need to do a double prime. So double prime would be minus, right? Okay. So here I got minus 3a, right, from here. I'll write for now, and then I'll tell you. Sine 3t, and then plus, right, 3b cosine 3t, right? But then I pick up also from here, right? When I differentiate a t, I pick up these guys too. So in other words, right, what do I got? In terms of sine, I got minus 6a, right? In terms of cosine, I got 6b. Okay. And now then I only have to differentiate the t term, which is here I got minus 9a cosine 3t minus 9b sine 3t. All right. And so notice that part of the art here, if you want to call it art, is to organize the terms and keep track of it efficiently. Okay. If you don't, then you will write down, like I said, like more terms than what I wrote. And it's just, you understand, the more terms you write, the more chance you will make an error. So that's where, keeping track of things efficiently is a very helpful device in this case. Any question? Yeah, we can. Yeah, after this. Any question on this? Oh, there's an error. Is there? Where's the error? What's the error, Saga? You mean here and here? Yes, it's 3. But when you differentiate with this, you pick up these terms. Yeah. Still think I'm wrong? Okay. That's anyone else think I'm wrong, or the rest seem okay? Anyone else? I'll need another tie-breaking vote. Okay. Democratically, I will trust the majority. All right, Sagar? Even though you can feel free to think that I'm wrong, but I'll go with the majority. Okay. All right. So plug in. Plug in. What do I get? So yeah. Also, I think go back to what Carl said, right? The t term should cancel. Is it? Beautiful, right? Beautiful. That's a very good sign that we are on the right track, right? And so what we got left is just minus 6a sine 3t plus 6b cosine of 3t is equal to sine 3t. That's interesting because that means that A is minus 1/6 and B is equal to 0. I didn't expect this, but that's why it is. Okay. So our final solution, right, is y of t is c1 cosine 3t, c2 sine 3t minus 1/6 t cosine 3t. All right. Now I have to solve for c1, c2. Plug in y of 0 is 1, which is what? C1. Oh, that's beautiful. Y prime of 0 is minus 3c1. Oh, I don't need to care for that because that will be 0. So I got 3c2. Differentiate with the t term gives me minus 1/6. Oh, sorry, minus 1/6 times, yeah, the t term. And then that must be equal to minus 1. And so C2 is blah, blah, blah. Any question? Seems okay? So, right, these are 2 examples out of, so many variations that you can see on the problems. So back to Carl's request on complexification approach. Right. So what we got? So complexification, right, is the same for YH, and it will change, right, with the YP approach. So we will complexify, right, the forcing function. In other words, we'll do y double prime plus 9y is e to the 3it. Okay. And so our yp, right, will be, so I guess tilde, right, because this is going to be, we're going to extract the sign, right? So we're going to extract the complex part out of it. So anyway, right, y tilde p will be a, right, t e to 3it. Okay, that's y tilde. Differentiate. So y tilde prime is a e to 3it, right, plus 3ai e to 3it. Y tilde double prime is 3 AIT with that would, so that would be 6 AI e to 3IT. And then, oh, sorry, right, there's a T here, right, T here. And then differentiate with the other one gives me not minus 9A, right? Minus 9A T e to 3IT. Okay. So again, right, notice a very common pattern that when you plug in, the T term cancel, right? Plug in, what I get is 6AI is equal to 1, right? So A is 1 over 6I, right? Now, notice, right, we're in complexification, so we need to convert that back into, we need to convert that back into, the usual form, right? So which is minus I over 6, right? Wait, there I made a mistake. Shouldn't the first term's coefficient for y tilde double prime be a 3? You exactly do the same mistake as Sagar. I mean, not mistake, but you're okay. So there's a 3i here, yes, but there's a t here, right? Don't forget the product rule. So that plus that is the 6, right? Am I wrong? You know what I'm trying to say? So again, I'm doing it a little bit quickly, yeah. But if you do it the way you usually do, which is fine, then you have to keep track of 3 terms and you have to write one more line. Nothing wrong with that. It's just in my experience, it tends to, make you really, cranky and write down too many terms. So I rather just keep track of things in my head, grouping the terms together efficiently. But if you feel like writing everything down, go for it. Okay. So, all right, now I need to take the complex part, right? So nine, so AT, right? So y tilde P is minus I over 6 e to the 3it, right? Which is minus I over 6 cosine 3t plus I sine 3t, right? And remember, we take what? We take the complex part, right? Yp will be the imaginary part of y tilde. So that will be minus 1/6. Oh, sorry, miss a t, right? So 1/6 t cosine 3t. Yeah. Thanks, Will. Yep. Right, because again, right, this is because forcing function, right, is sine. And that's exactly right, the same thing as what we got above. Any question? Oh, good. It's a principle. All right, that's this. So the principle, right, or claim is like this. Is that if you look at, right, let's say a system, a y double prime plus b y prime plus c y, let's say is cosine omega t, a y double prime plus b y prime plus c y is sine omega t. Okay, like this. Let me call this yp1, yp2, yp3. Then yp1 is the real part of yp3, and not cube, right? Just a third system. Yp2 is the imaginary part of yp3. And you see why? Because this is cosine omega t plus I sine omega t. Is it okay, or you need more proof? We're good? Yeah. Okay, so moving on to physics. You're good with the math? Okay, so with the physics, actually, I think a good place to start is actually section 4.4. Okay, where what they give you is something very nice like this. They consider the system y double prime plus py prime plus qy is cosine of omega t. Okay, that's a system they consider. And never mind, well, never mind is too much. But for this system, I'm not going to test you on it. I think it's going to be quite enriching if you can appreciate what's going on here. I mean, again, if you have to something to do with these kind of things. But like I said, right, the above is the math part that you're responsible for the exam. Yeah. Okay. So here, the claim, right, and a very quite nice claim about it is the particular solution to this system, okay, the YP, will always be of this form, A cosine omega t plus phi, where A, right, has a explicit representation like this. And the angle phi satisfies this. Okay. So that's the main claim of 4.4. And so for those of you who do something in between math and physics, or you're interested in modeling, then right, you want to pay attention to this in the following ways. First of all, the derivation of this is interesting in and of itself. Okay, it's the technical mathematical part, but also it's the most tedious thing because after you do this, it's just really boring work of matching the math, right? The math will lead you to here. But I guess the interesting part about reading this or interpreting this, right, is where you make sense out of all these symbols and stuff like that. So first of all, right, making sense out of this requires several things. This is, first you have to pay attention. This is not the usual system that we're looking at, right? The usual system we look at, and by the way, I quote the Spring math system is my double prime, right? Plus by prime plus ky is equal to 0. Not 0, right? Is equal to, let's say, cosine of omega t, let's say, right? So comparing, right, here and here, for example, then you see what is the P and the Q in the system comparing with this. The P, right, is obviously B over M. And the Q is K over M. So whatever, right, the form that you're reading from here is kind of assuming that the mass of the object is going to be 1, right? Which kind of is okay, but right, when the mass gets really, really big, who knows, in a system, then that will affect, right, how these coefficients behave. So that's something you want to pay attention to begin with. All right. Also, right, the A here, right, is done assuming the mass is 1. So the A in general, right, the A in the coefficient here will be modulated, right, by, let's say, the A prime, A in this system, right, this A is going to be the other A over M, right? So first you want to pay attention to this. Second, right, so assuming, then we can read this system, right, as the system where mass equals to 1. And this is a spring constant, and this is the damping coefficient. Then what can you say about the behavior, right, of the solution as, these parameters change in value and in relation with omega? So one thing, right, let me say one thing right away too, is that, so without loss of generality, or, let's say assume, right, that mass equal to 1. And then, of course, right, P and Q are positive. One thing that's very important, and I insist, right, that you appreciate this if you look at physics system, is we showed that the homogeneous part goes to 0. Doesn't matter what the initial condition is and what P and Q are, as long as they're both positive. Because in the presence of damping, the homogeneous solution without forcing will always go to 0. Okay, so this you can call it the transient part of the solution. Okay, because your solution, right, will be composed of the homogeneous and the particular. So if you let the system, right, oscillate for a long time, then as time goes on, the transient part dies away, and all you have left is your particular solution. In other words, in the long run, your solution will settle into this pattern. And that's why you want to pay attention to this. Okay, so one thing. Now, the second thing is, looking at this, right, what do you observe? Anything in particular about that catch your eyes? Q equals to omega is important if, right, I don't think Pythagorean plays a role here, Daniel, even though what you say is right. I'm not so sure Pythagorean plays a role here. But Q equals to omega is good, but that's not really it, right, Matthew? What is that you want to say in together? Q is close to omega and P is small, right? If the closer Q to omega is and the smaller the P is, then the more A is pushed to be large. Okay, and so exactly, right, I guess the Q part close to omega, Q is the spring constant, right? But P is what? P is the damping coefficient, right? So this again reinforced this idea, right, that in the presence of the damping coefficient, yeah, but we want to be a little bit more careful, right? We can go back and look at the homogeneous solution here and state more carefully. Okay, that's one. But yeah, exactly. When this is equal to 0, right? But yeah, so let's look at that more carefully. Exactly. But right, what I'm trying to say is, if as long as P is non-zero, you see, then clearly A is finite. right? As long as you have I guess non-zero is not right, right? Positive, because this is damping coefficient. As long as there's damping, then you do not have oscillation that goes to infinity. And that's at least, right, one message, okay? Another message is exactly right. The lower the damping, and I guess the closer the Q is to omega, the more, right, the more amplitude you get, right, when the time goes on. Okay. And so, right, this equation, the A part, provides a very nice interaction between your long-term oscillation and, right, I mean the coefficients here in terms of the frequency of the forcing function. The phase shift, right, this is the phase angle. I don't think it plays much of a role, because that's just, basically how far away from, zero you are. It's just a translation of the curve. I'm not sure if it has any physical importance. But here, right, I think I like this term a lot. Okay. Now, okay, so if you want to understand resonance, right, more precisely. So again, right, what is resonance for us? Resonance for us, right, is that when you have a system, right, let's say my double prime plus by prime plus ky, right, is equal to something. So first we look at the homogeneous solution, right? So m lambda square, right, plus, oh, sorry, uh, resonance, right? So we don't have this. We don't have this, right? So it's just that, right? Because if as long as there's a forcing, as long as there's a damping coefficient, right, then we won't have. Then we're in this case, right? So m lambda square, right, plus k is equal to 0, or, right, lambda is plus minus square root of k over m, right, I. So the homogeneous solution is cosine of square root of k over mt c1 sine square root of k over mt. No, right? Because you know why? Because it comes from f equals to ma, right? So my double prime is f. So the whole point is, right, the forcing, the spring force is minus ky because it acts in the opposite position from, opposite of the displacement away from the spring. But damping also does the same thing, right? In other words, it acts in the opposite direction of the velocity, right? Or, you know, so the sign must be this by the physics. That's how we understand damping, right? It acts in the opposite of how you move, or whatever that is. So no, right? It's weird. Hold on. Let me phrase it correctly. It's not about direction, right? What this says is what? That if you are accelerating, no, not what if you are speeding up, right? If you're speeding up, then acceleration works, sorry, damping works against you. If you're slowing down, then accelerating, then damping works for you. Does that make sense? How should I say it? I mean, basically, I'm saying, right, of course, if y prime is negative, then minus by prime is positive, right? And if you y prime is positive, then minus by prime is negative, right? That's all I'm saying. But y prime being negative means you're slowing down, right? So I'm not sure how to interpret that in terms of damping. But I mean, this is what the message is. If anyone can put it in a better way, feel free to contribute. So you mean you're asking if there's something that works like this, plus? Not in motion, I don't know. Not in terms of motion, right? I mean, again, I think, right, when you're speeding up, I think, right, the drag force is working against you. I can see that. If you're slowing down, um, but yeah, I don't know if in terms of motion I see anything like that. Like again, I think you have to interpret this in terms of the acceleration. So, but yeah, I think this minus makes sense to me. I'm not sure there's a plus. Yeah. So you mean overall, right? Basically, then you have a plus, right? So that could be the case, but that I don't think is a natural, that would not be interpreted as damping, right? That would be something else. Yeah. So damping, again, in the proper sense of it, is whatever the effect is that works like this, right? Okay. So anyway, you go back to the math is that this is your homogeneous solution. So exactly, right, when omega is equal to square root of k over m, that you have resonance. And by the way, right, this is called the natural frequency of the system. So 1 second, I think Matthew, right, was saying that Q is close to omega in this case, and P is equal to 0. So of course P equal to 0, that takes out the damping, but I think, so here, right, if M equals to 1, so I think that says that omega is square root of K, is what I'm trying to see, what I'm seeing. So I don't see a square root term in here. Oh yeah, omega. You know what? I'm sorry, I wrote down the wrong formula. Q square, omega square, yeah. Omega square, that makes complete sense now, omega square, okay, like that. So if Q is close to omega square in this problem, right, and P equals 0, then you got resonance. But that's exactly the case when M equals to 1 that we're saying. So in general, right, is this. All right. And what is resonance, right? So resonance means that the solution, right, tends to, so basically resonance means that, right, exactly when omega is equal to this, right, because omega is equal to this, then your yp will have to take on this form, right? T a cosine omega t plus b sine omega t, right? So your yt in general will be yh, which is cosine sine, plus t like this, right? So this is purely cosine sine. So when you plot the graph, right, of your solution, so basically, right, it's going to be a linear envelope. And then your solution will oscillate, right, wider and wider because of this component. And that's exactly what we mean by resonant, right, in this case. So resonance, right, in physics is in mathematics, the coincidence of the homogeneous solution with a particular solution guess, right? And also the implication here is, at least for this system, is, of course it goes to infinity, but the rate of it going to infinity is a linear rate, okay? I don't know if that helps in any way because it still blow up, but right, at least this blow up is not as terrible as this kind of blow up, for example, a quadratic, right, explosion. The explosion here is a linear explosion in terms of amplitude. Any question? Okay. So the second phenomenon we want to talk about is the phenomenon of beat. Okay. So beat, let me say, right? So first of all, what is this phenomenon? So we're still considering a system where we have no damping. So in other words, you have y double prime, let's say this, plus ky is cosine omega t. Okay. And then the homogeneous solution is C1 cosine omega 0 t plus C2 sine omega 0 t, where omega 0 is square root of k over m, right? And so we're interested in knowing what happens when omega is not omega 0, but omega is close to omega 0. All right. So, right, not resonance, because these are different, but quite close, quite close. Okay. So what happens is mathematically something like this. All right. Mathematically, what happens is, let me see here. So mathematically, what happens is, let me give you an example. All right. So let me look at an example. So, okay, hold on. So the phenomenon, right, is like this. Let me just say the phenomenon first. The phenomenon is that you have an oscillation in terms of the amplitude. Like this. Where your solution oscillates in between this. So basically, you see a oscillation of the amplitude of the solution with some observable long period. Okay, so this envelope right here is the beat. So I think in music, I'm not very familiar with it, but basically in music, right? Imagine you listen to some signal, but then it gets loud, and then it gets more quiet, loud, quiet, loud, quiet, like that, right? So the oscillation itself creates the music, but the amplitude, right? The loudness or the quietness will have a pattern, and that's the beat. Does anyone else have any better example of how the beat behaves in music or in some other phenomenon that you want to share? Uh, that's a really vague statement, because anything that has oscillation will be related to Fourier transform, right? So that doesn't say anything, I think. But like again, right? Notice, so let me go back to the book and show you. So this is beat. Okay, this is resonance, and this right here is no beat, or like this, right? And I hope you see the noticeable difference of the pattern of a signal, right? And I guess let's not consider this because this is resonance. But suppose you hear a signal, I'm sure, right? Your ear will pick up the difference between this and this. Okay, and again, right? It's the pattern of the signal. It's not about anything else. So what I'm interested in is like describing something out there in real life that you observe this pattern rather than this pattern, right? But the point is, right, the difference between this and this is caused by how close the natural frequency is to the forcing function. That is, right? If the natural frequency is quite close to a forcing function but not equal exactly, then you have a signal like this. Okay. So what I want to show here is just an explanation on why this envelope, or how mathematically you see this envelope is shown, is full. That's all. So mathematically, right, to see that this happens, okay, to see that this happens. So the same thing, what I'm interested in is to show you that the math captures the physics in this way. So resonance for us, for the math, is the T term right here, okay, which leads to explosion of the system in physics. So mathematically, right, what caused the envelope here? So I'm just going to quote the book wholesale. Basically, they look at the example where you have y double prime plus 2y prime is cosine of omega t. Okay, and they look at the initial condition y of 0 equals to y prime of 0 equal to 0. All right, so the initial condition serves to make the solution simpler, so you can consider what's going on. But after after you plug in and solve, then you get so your solution to this system will be y of t, which is a cosine of omega t minus cosine of square root of 2 of t, where a, right, this a is the a where you guess the a comes from the guess of the particular solution. Ypt is, whatever, right? A cosine omega t, I think. All right, but so I'm not interested in what exactly the value of a is, but I'm interested in the rewriting of this form right here. So basically, after you solve for this, you get your solution to have this form. Now, what happens is you can rewrite this in terms of the difference of cosine, right? So the point is this, that you have cosine of a minus cosine of b, right, is equal to 2 sine. Like that. Okay. So what happens is that in this case, your solution can be written as y of t to be a, sorry, I think I missed a minus here or something like that. So basically your solution will be minus 2a sine of omega plus square root of 2 over 2 times t, and then sine of omega minus square root of 2 over 2 times t. Okay. And this right here is exactly what explains the beat. When omega is close to square root of 2. Okay. Because, right, notice this is the system when mass equals to 1 and spring constant equals to 2. Okay. So the omega 0, right, the natural frequency in this system is square root of 2 right here. So when omega is close to square root of 2, but not exactly square root of 2, and of course with the system initially at rest, this is your solution. But the point is, right, in this form, you can see that the beat forms like this. How do you see that? Basically, you can review this as this, right? Ignore this for now. This term doesn't matter so much. But basically, this right here is your oscillating amplitude. This is the outside envelope. This is what, and this is the inner oscillation. Okay, because if omega is close to square root of 2, this is going to be a sine with very long period. And of course, right, this is going to be a fast frequency, high frequency, right? This is a low frequency amplitude movement, and this is a high frequency, the signal movement. So looking back, right, this right here, right, this envelope is exactly the sine of, roughly speaking, omega minus omega 0 over 2 times t. That the beat is formed by the slow period, small frequency, long period movement like this. And the inner movement is because of the fast frequency in the difference. Okay. So by analyzing, right, so the interaction between the homogeneous solution and the particular solution together, right, by the difference of the cosine formula creates two sine function, for example. One of them will be slow and one of them will be fast. The slow one, if it's very slow, it will create an envelope. And the fast one will just be the regular oscillation. Any question? Okay, so that's all the physics I want to say. All right. Now, moving on, let's see. The plan for the rest of the class, right, is this. I definitely will want to cover 5.1, which is linearization of a system with non-constant coefficient. All right. And that may take us half a class maybe. Beyond that, right, there's this so-called difference equation, which I don't know what topic that is. Let's see. Difference equations is I think chapter 8. I'll take a look, all right. But basically, it's about the discrete when the time is discrete. So this is the discrete, you know. So instead of discrete time period, okay. So instead of having time as a continuous random variable, in some system you have discrete time period. And so for that, right, the technique of calculus doesn't apply anymore. But the way the way that we think about how to solve this equation, like the characteristic equation, still works in this case. Okay, so it depends on how much time we have. I'll say something about this. But in terms of material, right, definitely we'll cap everything for the final exam after 5.1. I mean, up to 5.1. All right. So this is something I'm interested in discussing, but not enough time or discussion to do justice to it. So the material, right, for you until the end of the class will be 5.1, right? This is the final cap. Okay, so this is extra. So that's the plan for our last class, right? Which is next Tuesday. We only have one class left, right? Is that right? Yeah, for the final exam. Wait, we have two more or one more? Oh, so I need to go back on that. I thought we only have one class. If it's two class, then okay, sorry. I thought we only have one class. If we have two classes, then the difference equation material will be on it. So sorry, Anne, right? So that's the wrong information. If we have two classes, then I do have time. I do have enough time to cover something here. So go back here. Sorry. Then the final cap is something along this line. So go back. So I definitely will have to review this material. So the final will include something here then. Okay. Sorry. So review session, yes, I will ask the TA, right, to let you know when the review session will be. So my experience is we do like about 2 sections in here in some of the basic techniques in terms of difference equation. Okay. So 5.1 and some section in chapter 8 is what will be the material for the final cap. I'll tell you more exactly after we have a better idea next week on how the timing goes. Depends on how much time I have to properly cover these materials. Then I'll talk about how much material will be on the final exam for that. Yeah. All right. So I think it's good to stop here, right? Next time we'll pick up 5.1 and then move to chapter 8. That's right. 3 hours. Thank you. You too. Thank you. I do. I do, but only this semester. Every fall semester, every fall semester is going to be offered again. Discrete time period. I'm usually the professor, but right now they're offering two classes. So there's usually one more, either Professor Casper or Professor Weston are the other ones. So maybe next time around there could be another professor. But I think right now the department is offering two sessions. So the chances are I'm the professor for one class. Yeah, one session. Yeah. Yeah, Matthew, logistic equation, right, is just describing first order, right, y prime equals to ky kind of thing. But I think this, so the point is actually for every differential equation you can come up with, there is a corresponding discrete system, this discrete time and analog. Okay, so you could have a first order difference equation, or you can have a second order difference equation. So in that sense, right, saying logistic equation is too narrow for the difference equation consideration. So I mean, you could have something like this. Maybe that's what you're thinking of, which is very simple. Let's say yn is, k times yn minus 1, right? That's the first order equation. But you could have something really more complex like yn, right, plus 2yn minus 1 minus 2yn minus 2 is equal to 0. This is a second order equation, right? Because you have the difference of two periods coming in. And then you can just generalize it to many extra, right? And then you could have, whether this is equal to 0 or equals to, I don't know, a number like 3 or 4, and then a function of n, for example, to make it like non-homogeneous, right? Many variations. So the point is, right, that the difference, so this is a second order difference. No, Saga, 4.4 is not on the exam. Overshoot, what do you mean by overshoot? Oh, so yeah, class is over. So it's 6:20 already, right? Why early? So that you talk about uniqueness, right, of solution, or you can talk about a convergence of solution. That's a different thing, right? So you can have a system like this, right? If k is, let's say k is less than 1, then maybe the solution goes to 0. So that's a different thing, right? That's a convergence of solution, right? A convergence of solution. But if you talk about crossing equilibrium solution, that's a different thing. So all in all, right, this is why, like, you need a proper treatment on the discrete time solution. So in other words, right, whatever concept we have from the differential equation, right, what can be said in the analog of the difference equation. But I'm not so sure if you're talking about, like, the long-term behavior like this, right? Or you're talking about the uniqueness of solution, which kind of, I know they're related, but they're not the same phenomenon, right? So the crossing is yeah, right. So I think we don't have time to discuss this so much. That's like, the long-term asymptotic behavior. What we will focus on is how to solve this equation, like the characteristic equation, what's the form of the solution, that kind of thing. So in the spirit of more like chapter 3, chapter 4. Yeah. No, that's too much. That's not enough time for this class. Yeah. Okay, yeah.